Welcome to module 43 of Database Management Systems course in the IIT Madras online BSc program. We have been discussing about indexing and hashing, and we have recapitulated binary search trees, particularly the balanced ones in the last module. And specifically, we took a look at a new interesting data structure called 234 trees as a precursor to what we are going to discuss today. So, 234 trees have 3 different types of nodes and has a unique property that all leaf nodes are at the same level with respect to the root. So, that is very useful, and we will extend that idea in terms of B plus tree and its use in index file and normal record files, and also look at the B tree versions of it. Now, coming to B plus tree index files, first let me quickly introduce through a simple example as to what a B plus tree is. So, and we will have more actual database oriented example later on, but just to define, it is a B plus tree is a balanced binary search tree, right. So, it will always have a height of some log of the number of nodes. The base of that will be decided, but it will certainly be more than 2. So, it is being called a balanced binary search tree because it uses the same concept, but it necessarily is not a binary tree. It follows a multi-level index format like the 234 tree, has a leaf nodes denoting the actual data pointers, and all leaf nodes are at the same height. This is the important thing. All leaf nodes are at the same height, and the leaf nodes are also linked. Leaf nodes are also linked via a pointer, so that you can use the indexing structure to access it randomly. You can also use this linked structure for a sequential access. Naturally, as the construction will ensure that the keys in the leaf node are in sorted order. So, couple of properties, but exactly like the 234 tree, only that here we do not have the restriction of having one node, a 2 node, 3 node, 4 node. All nodes are of the same type, but they may have variable number of data key elements and variable number of pointers. So, this is the basic structure. Now, naturally, to keep it variable, what we do is there is a trade off, because the more number of nodes you can keep, more number of keys you can keep in a node will certainly mean that your height gets less, obviously, because. So, if we have more number of nodes, then every node becomes a lot more big in size, and it may not be possible to bring it to the memory and fit it there, because the computations. So, it may exceed that block size. Also, if I have more number of keys in a node, then within a node, like in the 234 tree, think about a phone node, there are 3 keys. So, multiple comparisons are required sequentially to find out what are the 2 keys between which your search key is actually to be expected. So, if we increase the number of keys in a node, then that linear search part increases, even though the height is reducing. On the other side, if we have nodes which have very few keys, then you will need lot more number of nodes, and the height will go up. So, and obviously, the storage will also be more. So, to strike a balance, we have a very nice rule that in every internal node, like this is an internal node. Of course, this is very special because it is root also. In an internal node, at least n by 2 record pointers must be there, where n is the maximum number of keys and pointers that a particular node can fit. So, n is that number. So, of the possible number of record pointers with keys that it can fit, it has to be at least n by 2 must be there, and at most naturally n can be there, right. So, when n are there, then it is totally full, but it has to be at any point of time at least half filled. Naturally, the exception is the root node, because root node is starting. So, at the beginning you may not have enough keys that have gone into the tree. So, the root node, it is possible the root node will have very few keys. In the leaf node also, there has to be n by 2 record pointers and n by 2 key values that finally you have found. Naturally, it will be full if this value goes up to n, and then it will need, say this is a leaf node. So, in this you need a additional pointer to the next leaf node, additional pointer to the next leaf node for the linear search. So, that is the basic structure of a B plus tree. So, how do you search? Very simply, as we did in case of 2, 3, 4 tree. Suppose in this given tree I have to search for 55. So, I will start with the root, compare with 25 it is more, compare with 50 it is more, compare with 75 it is less. So, this is going sequential. So, it is in between these two 55. So, I follow the corresponding link. So, I come to this leaf node and I check with 50, it is more, I check the next one 55, I have found it, right. So, that is the. So, there is one linear here, this one linear here, and then depending on the range you will get to the next level, right. So, I am just showing one level here, and here since the key itself is the data, there is no separate pointer in the leaf node to go to the data. In general, in an index file structure, that pointer at the leaf node will also be there. So, if I have to insert, what do I have to do? Suppose I have to insert 60. Right. So, I will start searching here this, and I will find that this is expected here. Then I search here, less, this is more. So, I know 60 should go in at this point, and I am deliberately showing a case of a node being full, right. So, this nodes can accommodate, let us say 4 keys only, and you have a fifth one. So, it means that this leaf node now have 5 keys expected, and and its current root is 50, that is from here, like the current root of this is 75, that is the list value element in that, list value key in that. So, I will have to split, right. I have to split the node and split and do what? Create a new root and push it to the previous level, right. We did all that in the 2, 3, 4 tree. So, we split into 2, let us say there are 5. So, almost half of, and so as we do that, 50 is a root here and 60 is the root of the new leaf node that has been created. So, 50 stays as it were, and 60, the new root, has to get inserted in the parent, which is a root node. So, earlier we had 25, 50, 75 and null. Now, you have inserted 60 here, which is also a linear insertion. You insert 60 there and make its pointer point to the new leaf node, which has. So, the values have been split in half. I said this will guarantee, because when are you splitting? When the leaf node already has n items, right. So, you are trying to insert one more. So, you are in n by 2. So, what will this necessarily mean? That if you split, in one you will have n by 2, in the other you will have n by 2 plus 1. So, here we have 2, here we have 3, which is, and it will always guarantee, by going by this rule, it will always guarantee that a node has at least n by 2 entries. Similar thing will happen in the internal nodes also. So, if I need to insert something which will mean a split, for example, if I am trying to insert 85, say I am trying to insert 85, then 85 has to go here between this. So, which means that this has to now split as 75 80 and 85 90 95 like this. So, this 85 has to go into the root node after 75, but there is no space for that. So, this has to split again as 25 50 and as 60 75 85. Okay. So, I will have a new root node which will have 25 the first key, 60 the second key, and we will have null in the rest, and this will point here and this will point here, right. So, this way it propagates wherever this happens. So, that is the basic insert process. So, as you have the insert, you can easily extend this for delete. Only thing you will have to do in place of delete is to, when you delete, you have to first search, delete that, and you will have to, if it is a root of that leaf node, then it will get deleted up above the whole tree. That is one part. And the second is, you will have to reorganize, because by deletion, if a node falls below, so your cutoff value is n by 2, cutoff value is n by 2. So, if it falls below n by 2, you have to check whether it can be merged with the adjacent node, leaf node, and adjust it. The same thing will happen for the internal nodes also, and the height might collapse. So, you can see that with the height can only increase if I have an insertion, and it can only decrease if I have a deletion. In some cases, of course, not always. Oftentimes, insertion or deletion will not change the height of the key, and the property will be maintained that all leaf nodes are at the same height. That is the basic advantage, and that size will be log size. So, this is what is used for the index files. We will see they are used for the general record files also. So, they have the basic advantage is whatever we saw earlier, the performance of index sequential files we are seeing, they degrade as the file grows. So, many overflow blocks are created, reorganization is required, which is expensive, and so on. Whereas, this one B plus tree reorganizes itself. It is called a self organizing data structure. It is not, overall organization is never required to maintain the performance. And obviously, there are disadvantages of extra insertion, deletion over it, some space over it, but it outweigh the, this disadvantage is outweighed by the advantages it offers. So, it is used very extensively these days. So, here is a more more database kind of example for a B plus tree. You can see this is the data we are trying to keep, and where my the key being used for this organization is a name, right. So, we have this organization, and the root is having only Mozart, and these are internal nodes. Naturally, all nodes here will be less than Mozart, all nodes here and subsequently will be more than Mozart. These are internal nodes, and then finally, you have the leaf nodes, right. And you can see that in every internal node the keys are sorted. Similarly, in every leaf node the keys are sorted as well. So, if you see in the leaf node, in the internal node, it is always going to another internal node, the pointer points to another internal node or a leaf node, but in case of a leaf node entry, the pointer will point directly to the record data, right. So, this is where you will be able to find the data. The next one points to this data and so on, right. These are sorted within every leaf node and across the leaf nodes also, and you use an extra pointer to link them, so that if you want like select all kind of query where you want to go with the entire file, you can, you do not have to search multiple times, you just come to the leftmost one and keep traversing it sequentially, right. And this is where your actual data is kept. So, this is exactly how, and so what I was showing later, I have examples with this kind of extensive data also, but I have given you the basic principle of how the B plus tree will work as an indexing file. So, this is a formal definition again, which I have already stated to you. All paths have same length to the leaf, and the leaf has to be at least half, I mean every node has to be at least half filled, right, except for the naturally for the root node, and that keeping that exception aside, these conditions will have to satisfy. So, at every node what you have pointers, and you have keys with them, with keys satisfying this condition for linear search and ordering. Right. Now, in a leaf node you will have, besides you will have, other than the key, you will have pointers to the data, right, and the pointer to the next leaf node. We have already seen this. So, these are just more detailed illustrations to show you. So, in a non leaf node you will just have the keys and the pointers to other nodes. So, here is an example of a B plus tree index file. So, leaf nodes here are mandated that they must have 3 to 5 values, that is we are working with a n value of 6. So, internal nodes must have 3 to 6 values, internal node is n by 2 to n, leaf node is n by 2 to n minus 1, and the root must have 2 children. You can see that all these are satisfied and things are in order. So, you see that the internode connection is being done by the pointer. So, whatever is logically close does not need to be physically close. That was becoming that logical closeness is what we need for answering queries, values are closed and so on. Physical closeness we needed for index sequential file to put the things together. Here, by very efficient use of pointers, we are able to get rid of that physical logical contradiction. So, this necessarily, if you look at the non-leaf levels, it necessarily conceptually these are basically sparse indices, right. You can, because you are not keeping everything, you are just keeping selective keys, and as you go higher and higher you keep more and more sampled key values only as index, right. So, here some basic arithmetic is given. So, if there are k search key values, given that any node must have n by 2, at least n by 2 keys. So, it will have n by 2 pointers, that is n by 2 children, at the least it will usually have more, right. So, now your base of the logarithm becomes n by 2, right. But if it is more, the value actually will be less than k, less than this, but this is the highest possible value if all nodes have only n by 2, then this is for searching k keys where every node can contain n keys and pointers, you will need a height which is log n by 2 k. So, typically as k will be very large, so will be n, n will not be a very small number like 2, 3, it will be maybe 1000 and so on. So, you will get a very efficient height management here, right. So, that is the. Now, the rest I have given the formal statement of the algorithm in pseudo code of how do you do search, which we have already discussed. So, I will request you to study the algorithm and convince yourself that it works in a nice way. So, just to quote some typical values, if we have k as 1,000,000 search keys, I am sorry, and n is 100, then you have this logarithm to take 1,000,000 10 to the power 6, which is taken log of with the base 50 n by 2, and that value comes to 4. So, which means that in a general lookup you will access at most 4 nodes on that tree, right, quite a manageable ones. Right. Whereas, if you had a balanced binary tree with 1,000,000 key values, you will require around 20, because 10 to the power 3 is 2 to the power 10. So, 10 to the power 6 is 2 to the power 20. So, you take a log to the base 2. So, you get at least 20. So, you have a huge 5-fold improvement here, right. So, that is a core advantage. Now, naturally there could be duplicates in the search keys. So, there could be multiple of having the same value. So, we cannot always just guarantee a strict inequality, we will have to go with a relaxed form of inequality, and whenever the values are equal, we will have to see how there may be many of them which has to be linearly scanned. So, you can extend the procedure for search and consequently insert delete if you have duplicates in the data. Now, in terms of updates, insertion and deletion, I will not run through the slides, because it is just working out of an insertion example and a deletion example. So, starting from here, we have step by step shown how the different insertion steps will happen, what is being done at every step with these kind of examples. So, go through them carefully and you will understand. Similar example is also given for deletion. So, you can look at the updates due to deletion through this example, right. So, to study that and at home and get comfortable with this process, but the basic principle, as I have explained at the beginning, of insert and delete remains the same. So, what it gets us here is the basic index file degradation problem is solved by B plus tree indices. Data file degradation problem, where you actually keep the records, can also be handled by the same. So, B plus tree is used, it is typically called B plus index tree because it uses an indexing structure, but it can be used for our database index files, or it can be used for database record files, right. And leaf nodes will always need to be half full, as we had said. So, this is an example of this is the root node, these are internal nodes, and this is your leaf, where you have the data one after the other. So, you may have non-unique search keys, as I said, duplicates. So, it might, if you have too many duplicates, then there may be difficulties in handling that. So, some people use bucket it on separate block, which is I do not think is a great idea. You can have a list of tuple pointers with each key, like hanging a kind of chain there, or you can try to forcibly make the search key unique by adding a record pointer, record identifier, So, that will have overhead of extra storage for keys, but it will make insertion deletion coding simpler, and since this search keys are non-unique, it does not really matter which record you pull up, or possibly you are trying to pull up all the records, but having that key value. So, if you have this record identifier added to the key, then in terms of actual storage, it becomes, it has an overhead of storing that, but it makes the things fall into the same structure of insertion deletion, and that is why it is quite widely used. Another issue is if a record relocates, because you are having pointers, right. Finally, at the leaf level you are having pointers. So, if a record relocates, then the stored record pointers have to be updated, right. And this update is always expensive, because it might lead to your node splits, which are expensive. So, what is typically done is you use primary index search key instead of when you have a secondary index. I mean, this problem primarily happens with the, will happen for the secondary index. You have a primary index which actually organizes records, but you have a secondary index on that. So, if things change in the primary index, a record location changes in the primary table, then your secondary index will have to get adjusted, because it is using those pointers in turn. So, what you do, you do not use those record pointers, instead you use the primary index search key as if that is the identity, right. It should be, because it is a primary index. So, that will mean that you have some extra traversal cost, but queries will be a little bit more expensive, but in the overall performance, in the amortized performance is often preferred, because node splits are really cheap in this case. They are not as expensive as it would be if records relocate for a in the primary table, and you have multiple secondary indices to update. So, these are, then there is question of how do you index with strings. Strings could always be a variable length. So, it has a variable fan out, then you do not know how many will be there. So, one thing which is often done is the prefixing, that you use multiple strings and kind of code them in terms of their prefix, the starting value. So, you have Silas, you have Silvetsats, you can separate them by SILB, right, and put that as the key. So, this kind of compressions are also possible. Now, so that was about B plus tree. There is a compaction on B plus tree known as B tree. In B tree, the basic idea is unlike B plus tree, B tree will allow a search key to appear on the tree only once. Once it is in a B plus tree, it will appear multiple times till the root. So, you can see the contrast here. This is your B plus tree. So, you have Mozart happening here, then later on happening here. You have Einstein happening here, and then happening here, and so on. But in a B tree, you will have them only once. So, Einstein is here. So, Einstein's record in the leaf node will not have another entry. So, you have a separate pointer right here for the Einstein record, for the Kurtz record, for the Singh record. So, once a key occurs in a node, you keep the record pointer right there, so that it does not occur again, like it is happening here. So that's a compaction. Only those who have not occurred on any internal node will occur in the leaf node. So this will naturally take less space to operate. So it uses less number of nodes, and you are at times be able to find a record even without going to the leaf node. Right. In B plus tree you have to go to the leaf node, only then you get, but here you might get it earlier. But there are several disadvantages that happen, like first of all, this advantage of finding a record earlier is not great, because only a small fraction of all keys will be on the internal nodes as it is. And non-leaf nodes are now getting larger, right. So, if the non-leaf node gets larger, the fan out, the number of possible children gets lower. The value of n is decreasing, because you have extra information kept in the non-leaf, which will mean that the moment you reduce the fan out here, the height of this B tree will increase, right. So, also insertion deletion gets more complicated. So, it is typically that the advantages of B tree do not outweigh the disadvantages it has. So, the concept has been around, it has been used, but it is not a very popular structure. So, this brings us to the end of this module. We have discussed about B plus index files for index as well as for keeping the primary data, and we have familiarized with B tree index files as well. Thank you very much for your attention, and we will meet in the next module.